You've heard this 1,000 times. Nothing escapes a black hole. Not matter, not light, not information, nothing. Once something crosses that boundary, it's gone forever. Trapped, swallowed, erased from the observable universe. That's the story, right? That's what everyone knows. Fine, so explain this to me. How do we have a photograph of one? In 2019, astronomers pointed a network of radio telescopes at a galaxy 55 million light years away and produced an image. A black hole right there. Orange ring, dark center, front page of every newspaper on Earth. But wait, if light can't escape a black hole, how did light from that black hole reach our telescopes? If nothing gets out, what exactly are we looking at? Here's where it gets worse. Think carefully about what light can't escape actually means. It means no photons are leaving, none, zero. And photons are how you see things. When you look at a tree, photons bounce off the tree, enter your eyes, hit your retina. That's vision. That's detection. No photons, no detection. So, a black hole shouldn't look dark. Dark is what you see when there's very little light. A black hole should be invisible. Not black, not shadowy, not ominous. Invisible, a perfect absence. No photons means nothing for your eyes or your telescopes to collect. There's nothing there to photograph. Yet astronomers do far more than photograph them. They measure black hole masses with extraordinary precision. They calculate how fast black holes spin. They watch black holes rip stars apart and consume the debris over months. They track pairs of black holes spiraling toward each other. They detect the collisions. How do you measure, track, observe, and photograph something that by definition cannot send any signal to your instruments? The question isn't just, how do we detect black holes? That's the shallow version. The real question is deeper. What does detection even mean when the thing you're detecting is fundamentally, physically, mathematically incapable of being observed? And here's what I want you to understand. The answer to this question doesn't just explain black holes. It reveals something profound about how we know anything in physics at all. Let's start by killing your mental image of a black hole. You're picturing a cosmic vacuum cleaner. This giant mouth in space sucking everything in, gobbling up stars and planets and light like some kind of celestial drain. Wrong. Black holes don't suck. They don't reach out and grab things. They don't pull any harder than any other object with the same mass. Now look, if you replaced our sun with a black hole of identical mass, Earth's orbit wouldn't change. We wouldn't get sucked in. We'd just freeze to death in the dark, still orbiting exactly as before. So what makes black holes special? They curve space-time. Every mass curves space-time. That's what gravity is. But black holes curve it so severely, so extremely, that something strange happens. Past a certain distance from the center, all paths lead inward. Not most paths, all of them. Even the path light would take, even the path pointing directly away from the center. Space itself is so warped that outward doesn't exist anymore. That boundary is called the event horizon. And here's what you need to understand. The event horizon is not a surface. It's not a wall. It's not a thing you could touch or see or bump into. It's a mathematical boundary, the point of no return. Cross it, and every possible trajectory through space-time leads to the center. You're not being pulled in. You're just in a region where all directions are in. Now here's the key insight that changes everything. Only the inside is trapped. The event horizon is a one-way boundary. Things can fall in, nothing can come out. But outside that boundary, space-time is curved, yes. Gravity is strong, yes. But light can still escape. Matter can still orbit. Information can still reach your telescopes. The black hole isn't hiding. There's no cosmic conspiracy to stay invisible. It's just that once something crosses that line, it can never send a signal back. Everything outside the line is fair game. And as it turns out, the outside is where all the action is. That's where the fireworks happen. That's where the universe screams. So if we can't see inside the event horizon, what are we actually detecting? The answer is violence. Pure, spectacular, universe-scale violence happening right at the edge. Now here's what happens when matter gets close to a black hole. It doesn't fall straight in. It can't. Conservation of angular momentum. See, anything moving even slightly sideways will spiral inward, not plunge directly. And as it spirals, it joins other matter doing the same thing. Gas, dust, sometimes entire stars ripped apart by tidal forces. All of it swirling together, getting closer, packing tighter, moving faster. This is called an accretion disk. And accretion disks are where physics gets violent. Think about what's happening in that disk. Matter is orbiting at significant fractions of the speed of light. Particles are colliding constantly. Friction everywhere. Compression increasing as everything funnels inward. Now all that kinetic energy has to go somewhere. It becomes heat, unimaginable heat. The inner regions of an accretion disk can reach temperatures of millions of degrees. At those temperatures, matter doesn't just glow, it screams. It radiates across the entire electromagnetic spectrum. Radio waves, infrared, visible light, ultraviolet, X-rays, gamma rays. A black hole with an active accretion disk is one of the brightest objects in the universe. Not despite being a black hole, but because of it. The extreme gravity creates the extreme conditions that create the extreme radiation. Let me give you an analogy. You're standing across the room from a bathtub. Someone pulled the drain plug. Can you see the drain? No. It's small. It's far away. The water's in the way. But can you tell exactly where the drain is? Absolutely. Because you can see the water spiraling toward it. The spiral points directly at the thing you can't see. Black holes work exactly the same way. The light reaching our telescopes isn't coming from the black hole. It can't. It's coming from the matter that's about to cross the event horizon. Matter in its final moments, heated to millions of degrees, radiating frantically as it spirals toward oblivion. We're not seeing the black hole. We're seeing everything around it dying. That's detection method one. We don't photograph the grave. We photograph the funeral. And the funeral is so bright it outshines entire galaxies. But what if there's no funeral? What if a black hole is sitting alone in empty space? No gas, no dust, no stars nearby to consume, nothing to heat up, nothing to radiate? Is it invisible then? And here's what most people completely miss. Light is trapped by the event horizon. Gravity is not. In fact, gravity is the event horizon. You see, the event horizon exists because of how mass curves space-time. And that curvature doesn't stop at the boundary. It extends outward, affecting everything nearby, bending the paths of anything that passes close, including light. This is called gravitational lensing. Light traveling from a distant star passes near a black hole. The curved space-time bends that light's path. From Earth, we see the star's image distorted, smeared, sometimes duplicated into rings and arcs. The black hole emits nothing, but we can map its location and mass by how it warps the light passing by. Then there are stellar orbits. At the center of our galaxy, astronomers have tracked stars for decades. One star called S2 orbits, an invisible point every 16 years, at speeds up to 3% of the speed of light. We can calculate exactly how much mass must be at that central point to create that orbit. 4 million times the mass of our sun, concentrated in a region smaller than our solar system. No light comes from that point, but the stars orbiting it tell us exactly what's there. That famous photograph of the M87 black hole, look at it carefully. You're not seeing the black hole. You're seeing a bright ring of superheated matter surrounding a dark circle. That dark circle is the shadow, the region where photons couldn't escape. We detected the black hole by detecting the absence, by seeing what wasn't there. And then there's the most spectacular detection of all, gravitational waves. When two black holes spiral into each other and merge, the violence is so extreme that space-time itself ripples. Those ripples propagate outward at the speed of light. In 2015, we felt them. Detectors on Earth measured space-time stretching and compressing by less than 1,000th the width of a proton. A collision that happened 1.3 billion years ago, sending shudders through the fabric of reality that we finally recorded. We don't see the object. We see its effect on everything else. And when black holes collide, the effect shakes the universe. Now, here's what I really want you to understand. Everything I just told you about black holes, it's not special. It's not some exotic exception that only applies to these extreme objects at the edge of physics. This is how all of physics works. You never observe anything directly, ever. Think about that. You don't see gravity. You see apples fall, balls curve, planets orbit. You infer gravity from the motion. You don't see the electromagnetic force. You feel your hand stop on a desk. You see lightning strike. You watch compass needles swing north. You infer the force from its effects. You don't see electrons. Nobody has ever seen an electron. You see tracks in cloud chambers, blips on detectors, current flowing through circuits. You infer electrons exist because something must be causing those effects. Physics is not the art of observing reality directly. That's the method. That's all we've ever had. We build instruments. We measure effects. We deduce causes. We test our deductions by predicting new effects. When the predictions match, we say we understand. Black holes are just the extreme case. The thing itself is not merely difficult to observe. It's mathematically impossible to observe. Nothing can cross back out of that boundary. No signal, no particle, no information of any kind. The black hole itself is fundamentally, permanently, absolutely hidden. And yet we know they exist. We know their masses. We know their spins. We know where they are, how they form, how they merge, how they affect everything around them. Because the effects are undeniable, measurable, precise. We know black holes exist the exact same way. We know anything exists in physics by what they do to the things we can observe. That's not a limitation. That's not a compromise. That's the method. That's how understanding works. The universe doesn't owe you direct observation. It doesn't owe you intuitive explanations or comfortable analogies. It owes you nothing, but it gives you clues. Bending light, wobbling stars, rippling space-time, screaming radiation. The universe leaves fingerprints everywhere if you learn how to read them. Black holes aren't hiding from you. They're not mysterious. They're not unknowable. You just had to learn a new way of seeing.